This is part 1 of Moon. We start with the key question. Moon overview. Earth's moon has been staring back at us for our entire existence as a species. And yet, for most of human history, we had almost no idea what it actually was. This is the first episode in our series on the moon. The core question we're asking today is simple. What is the moon? Where did it come from? And why does any of that matter right now? It matters because we're, right now, in the middle of a renewed push to return humans there. And understanding the moon from the ground up is the only way any of that makes sense. There's no previous episode to recap, because this is where the series begins. Let's start with the basics. The moon is Earth's only natural satellite. It orbits us at an average distance of about 384,000 kilometers, close enough to see with the naked eye in extraordinary detail compared to anything else in the night sky, yet far enough that light takes just over 1.25 seconds to travel between us. It's the 5th largest moon in the entire solar system, with a diameter of about 3,474 kilometers, roughly a quarter of Earth's own. Surface gravity runs at about 1/6 of Earth's, so a person who weighs 70 kilograms here would weigh just over 11.5 kilograms standing on the lunar surface. One orbit takes 27.3 days. The moon also rotates on its own axis in exactly the same time, and that synchronization is not a coincidence. It's the result of tidal locking, Earth's gravitational pull gradually slowing the moon's rotation over billions of years until the two periods matched. The consequence is that we always see the same face. The far side, often called the dark side despite receiving just as much sunlight, remained completely unseen by human eyes, until a Soviet spacecraft photographed it in October 1959. Before we get into how the moon formed, there's something worth flagging early, because it connects everything else we'll cover. The moon has almost no atmosphere. Almost, but not quite nothing. And that distinction, which sounds minor, turns out to have enormous implications for its geology, its temperature extremes, and its potential as a place humans might one day work. We'll come back to that. First, the origin story, because it's genuinely strange. For most of modern science, the moon's origin was an unsolved problem. 3 competing ideas were on the table. 1. The moon formed separately in the early solar system and was captured by Earth's gravity. 2. Earth and moon formed together from the same cloud of material. 3. A chunk of Earth spun off during a period of rapid rotation early in the planet's history. None of them fitted the evidence particularly well. Capture struggled to explain the moon's compositional similarities to Earth's mantle. Co-formation couldn't easily account for the moon's relatively small iron core. The spin-off hypothesis required Earth to have been rotating far faster than seemed plausible. Then, in the mid-1970s, a new idea emerged from 2 separate teams working independently. William Hartmann and Donald Davis, and Alistair Cameron and William Ward. Their proposal is what we now call the giant impact hypothesis. Roughly 4.5 billion years ago, a Mars-sized body, which scientists refer to as Theia, struck the young Earth at an oblique angle. The collision was catastrophic. It vaporized a vast quantity of material from both bodies, flinging an enormous debris cloud into orbit around Earth. Over time, that debris coalesced under its own gravity to form the moon. The model explains a lot. Theia's iron core mostly merged with Earth's, which accounts for the moon's low iron content. The compositional similarities between lunar rocks and Earth's mantle fit naturally. The angular momentum of the Earth-Moon system lines up. Isotopic analysis of lunar samples, particularly oxygen isotopes, broadly supports a shared origin between the two bodies. It's still not a perfect model. Questions remain about why the Earth and Moon's isotopic compositions match so closely if the Moon formed largely from Theia's material. Some researchers have proposed variations, a higher energy impact,
a faster spinning proto-Earth, or multiple smaller impacts. The giant impact hypothesis remains the leading explanation, but it's still being refined. The rocks brought back by Apollo missions, 12 in all, across 6 landings between July 1969 and December 1972, were central to working all of this out. Those samples revealed the moon's age, its composition, and the history of its surface in ways no telescope or robotic lander could have managed alone. Which brings us to the geology. From a distance, the lunar surface looks relatively simple: grey, heavily cratered, static. In the data, it's considerably more interesting. There are 2 broad terrain types: the lighter, heavily cratered highlands, the terrae, cover most of the far side and large portions of the near side. These are the oldest parts of the lunar surface, formed when the outer layer cooled and solidified from what's thought to have been a global magma ocean, somewhere between 4.4 and 4.5 billion years ago. The darker regions are the Maria, singular mare, Latin for seas, named by early astronomers who mistook them for actual bodies of water. They're not water, they're ancient lava plains formed by volcanic eruptions that flooded low-lying basins between roughly 3 and 4 billion years ago. The largest, the Ocean of Storms, stretches across an enormous area of the near side and is easily visible to the naked eye on a clear night. Beneath the surface, the moon is layered. There's a crust averaging around 50 kilometers thick, a mantle beneath that, and a small iron core with a radius of roughly 330 kilometers, significantly smaller relative to overall size than Earth's core. Evidence suggests the core has both a solid inner part and a partially molten outer layer, though scientists are still working through the details using seismic data from the Apollo era and more recent missions like the Lunar Reconnaissance Orbiter and Japan's Selene spacecraft. Volcanic activity appears to have largely ceased around 1 to 2 billion years ago, though some researchers argue smaller scale activity may have continued more recently. The moon today is geologically quiet, no plate tectonics. It does experience moonquakes, some fairly substantial, caused by tidal stresses from Earth's gravity and by the thermal expansion and contraction of surface rocks as they cycle through extreme temperature swings. And those temperature extremes are significant. Subscribe so you do not miss it.